Good morning. On Wednesday, we're going to work through another example on water gems, just because now you're on phase 2 of the project where you're going to begin doing some pipe sizing. So I wanted to reinforce that earlier demonstration. Please bring your laptop with water gems installed. It would really be a lost opportunity if you don't, so please do. Homework 8 is due on Friday of this week, and then looking a little bit further into the future, you will have another homework assignment due before phase 2 of the project. So it'll be homework 9 due on Wednesday of next week, and then the draft submission of phase 2 of the project is March 15th, and so that's Friday of next week. And I intentionally had that due before spring break so that you're not having that hanging over you during the break. I know you'll probably have other projects, and maybe I hope you'll be able to go do something nice as well during spring break, but that's the schedule for now. We're moving on to chapter 12 of the book. I hope that you're taking the time to follow along with that because it's an important resource and I think it's fairly concise. So if you're looking for additional ways to boost your understanding and be prepared for the exams, then reviewing the textbook and seeing how it explains this material, I think, is time well spent. Anybody have any questions related to the announcements before we move on to talking about energy in open channel flow? All right. Remember, Wednesday of this week is the career fair. So that's from noon to 4, and you should definitely take advantage of that opportunity. There's just never been a time when civil engineering was as hot as it is right now. You definitely have more opportunities, and so in just about any kind of discipline, every sub-discipline of civil engineering, they're looking for people. Every part of the country is looking for people. Every type of work, whether it's state agency, federal agency, contractors, construction companies, everybody's hiring. So you definitely want to capitalize on that and put yourself out there. So you should polish your resume, dress nicely, and go to that career fair on Wednesday. All right, this is a picture of water flowing through a channel. And my question to you is, how could we know what the depth of flow in that channel is? Well, I mean, obviously the easiest way would be to stick a tape measure in it and just measure directly what's the depth of flow. And so that's like easy to the point of being negligible. It's so easy. But before the channel is built, you can't measure what the depth of flow is going to be. So when you're designing the channel, you have to find ways to predict the depth of flow. And if we just look at this particular irrigation channel, it looks like it's concrete lined. And so we can't see the bottom of the channel, but it suggests pretty strongly that that's a prismatic and nice uniform channel, that it's been laid out on a consistent slope, that it's all, looks like this is concrete, so it's probably all concrete lined. You know, water is a precious resource in the Central Valley of California, which is where this picture was taken. And they don't want to lose water to infiltration. They want all of the water in this ditch to get up onto the crops. So the question, how do you determine what the flow depth will be before the channel is built? What equation do we use if, as is likely, the flow is steady? And I say it's likely that it's steady flow because this isn't like rainwater runoff from some watershed. So this isn't like a flash flood passing through. This is water in this channel has been pumped into it. So it's flowing, steady flow means that the flow rate isn't changing over time. You know, for maybe an 8-hour period, the farmer has rights to irrigate with this water, and through that entire 8-hour period, the flow rate's going to be the same. So it's steady because it's a consistent slope, it's a consistent construction material, the channel's prismatic, it's probably uniform. So what equation would you use to predict the depth of flow in a situation like this?
Manning.
That's right, Manning's equation. So let me write that on the board. Q equals area to the 5/3, slope to the 1/2, n value in the denominator, and then wetted perimeter to 2/3. Okay, so if you're a designer and you know you want a certain flow rate to be going through your channel, so that would be a given, Q would be a given. You know what you're likely to construct the channel out of, let's say concrete, so that defines the end value. And you know what the slope of the ground is, so that defines the slope. Then the area and the wetted perimeter are both going to be a function of the flow depth. And so if we had some trapezoidal channel and we knew the bottom width and we knew the side slopes, then y would be the only unknown. If we knew t and we knew the bottom width, y would be the only unknown, and we could calculate the depth of flow. But what if the slope was different than it is here? This looks like it's a pretty flat agricultural region. If we took this same trapezoidal channel, the same rectangular, same concrete material and the same flow rate, but it was at a location where it was a little bit steeper, let's say Idaho. That's another big agricultural region that's not quite as flat as the Central Valley of California. What if we had this in Idaho and the slope was more steep? So this is a relatively flat slope, and we've got a certain depth. If we take this same channel up to Idaho and the ground is more sloped, then the depth would be different. There's an infinite number of possible flow depths for the same channel depending on how you adjust the slope. And that's what we're going to be talking about today, is how we measure energy and the wide variety of possible flow depths that can exist for the same flow rate and the same channel configuration. So specific energy is a really important tool for analysis that we're going to use in open channel flow when conditions aren't steady and uniform. And in fact, we can apply it when conditions are steady and uniform. It's just that we don't normally have to because we've got Manning's equation instead. But specific energy is defined as how much energy is there relative to the bottom of the channel. Total energy takes into account the elevation of the channel above some datum, but the reason it's called specific energy is it means specific to the location where you are in the channel. So if we have a side view of some channel, so here's the bottom of the channel and here's the water, the specific energy measures the depth and then also the effect of the velocity head. Those two things comprise the energy above the channel at a certain point. So you can see it's the flow depth plus v squared divided by 2g, and then alpha is the kinetic energy correction factor, where if you have turbulent flow conditions, which is almost always, alpha is 1.05. If you have laminar flow conditions, which are very uncommon, then alpha would be 2. But this equation below it also reminds us that the velocity head term can be expressed in terms of flow rate. We saw that before earlier in the semester, where sometimes we'll say v squared divided by 2g. Other times, if we don't know the velocity but we do know the flow rate, it can be just simpler from a calculation standpoint if we express the velocity head in terms of q squared divided by 2g a squared. And why that's nice sometimes is, let's say that we had a rectangular channel, then sometimes we'll be solving for y, where y is an unknown. We can put the known flow rate in the numerator here, and then the cross-sectional area is also going to be a function of y. So it's just, it'll be a simplified way for us to calculate things when we express the velocity head in terms of flow rate. So it's the same thing. But specific energy is just saying, if we measure the water right here, what's its depth and velocity head, and then in the direction of flow, we can compare how much energy is there at one location to another. If conditions are steady and uniform, then all of the head loss that's occurring as the water flows downhill is equal to the changes in elevation. We've talked about that before. How many different ways in terms of velocity and depth could 10 cubic meters per second flow through this channel, which has a bottom width of 4 meters? So there's as many different possible flow depths as there are different possible slopes. We could have, for example, a really steep slope where the velocity is really high. You know, if it's really steep, like water slide steep, then the velocity could potentially be moving at 10 meters per second. Or if the channel is relatively shallow in slope and it's laid out on flat land, it could be that the water's just ambling along at a very slow 1 meter per second. So it would depend on the slope, but you could have any potential velocity. And remember that all of these different combinations we're going to look at have 10 cubic meters per second. And if Q equals V times A, then area, cross-sectional area, is the flow rate divided by the velocity. So if the water is moving at a really fast velocity, then it's going to have a relatively shallow depth because the water wouldn't need to be very deep if it's moving really fast at a high velocity to achieve 10 cubic meters per second. So we're just saying, like, what are the possible cross-sectional areas? And then if this channel is 4 meters wide, in order to get a certain area, we would just divide we would multiply 4 times the depth to get the area, or to get the depth, y, we would have the area divided by 4. So this is just saying, for example, if we had the 10 meter per second velocity, then you'd need a 1 meter square area to get 10 cubic meters per second. So if you just consider the units, 10 meters per second multiplied by 1 square meter is equal to 10 cubic meters per second. And then down here at the other end of the spectrum, you have a relatively slow velocity. The area there would need to be 10. I've blanked out some of these because given more time, I'd have you calculate these just to get the practice and the proof and so on. But there's an example that I'd rather get to later in the class, and so I won't have you calculate these values. The depths are shallow for the fast velocity, deep for the slow velocity. So you can either have water moving really fast at a shallow depth, or moving really slow at a greater depth, or somewhere in between. By the way, you know, all of these are relatively nice round numbers, but there's something unusual about this one, as you may have already guessed. You may have wondered, why did I pick 2.905 as the velocity? That'll become clear to you when I reveal the values for the specific energy. Because just although it's carrying 10 cubic meters per second, they're going to not have the same specific energy. The water's going to have different amounts of energy for each of these different flow velocities, because, like, where does E come from? Remember, the formula for E says take into account the depth plus the velocity head. So velocity head could be Q squared divided by 2G A squared, or it could be V squared divided by 2G. Either way, there's a certain amount of specific energy associated with each of these points. And what you'll notice is that there's a certain amount of specific energy that appears to be the minimum. So we could find out using Solver. We could, you know, if we had set this up in a spreadsheet, Solver has the ability to find out what is the value of velocity that gives you the minimum specific energy, if you want to minimize specific energy. Or if you're calculating the specific energy in terms of depth, what is the depth that minimizes specific energy? Now this is significant because the lowest specific energy, you can think of that as like the most efficient flow condition. And when we disturb the water, like if we put an obstacle in the channel, like going back to this irrigation canal, if we just dropped a couple of sacks of cement in this channel, when it wasn't flowing quite as deep. I mean, if we dropped the sacks of cement into this channel, probably it would flow over the edge. But if it had like half as much flow in it, it would pool initially until it had a certain amount of energy, and then it would flow over the obstacle. And this specific energy that's the minimum point, this critical depth, which corresponds to the lowest specific energy, is the most efficient way for the water to convey flow. So for a certain flow rate, for 10 cubic meters per second, like which flow depth needs the least amount of energy? So like at this 10 meters per second, you've got a lot of energy because the kinetic energy is really high. At the other end of the spectrum, when the flow depth is 2.5, look at how much specific energy you've got. Most of the specific energy at this end of the spectrum is because of the depth. And the velocity head is contributing very little. You know, it's only contributing 0.051 meters of specific energy. So over here, most of the specific energy is coming from the velocity head, and only 0.25 meters is coming from the depth. So more than 5 meters of energy is wrapped up in that velocity. But there is this minimum point, the lowest specific energy, and we call this the critical depth. So the critical depth is the depth that gives you the least amount of specific energy. So let's consider it from another perspective. If we made a graph, we could have flow velocity on one axis and flow depth on the other. So, I mean, I guess that's a pretty interesting graph, but it's not the really interesting graph. The really interesting graph is the specific energy diagram. And you're going to have to make some of these in Excel. And they're very useful for problem solving, for diagnosing the flow regime. Flow regime is a phrase you've heard before. On one of the homework assignments, I think you characterized the flow regime. Do you remember what you calculated? What number was it you calculated to diagnose the flow regime on that assignment? Froude number. Very good. So Froude number is one way to diagnose flow regime. These diagrams is another. So this is the ho-hum, kind of like boring diagram. But if we graph the specific energy on one axis and flow depth on the other, I mean, this is a very, very important figure. And there's a lot of questions we can answer with this figure. It looks simple, but boy, it's powerful what we can do with just graphing these details. So we'll kind of explore over several classes all of the things that we can assess with a figure like this. But all I've done is I've taken the data from the previous slide. So I took the E data and I put that on the x-axis, and I put the depth on the y-axis. So depth on the y-axis, specific energy on the horizontal axis, and then remember there was some depth that corresponds to the minimum specific energy. That's this point right here, that's furthest to the left. It's a really important point, the point of minimum specific energy. So this minimum specific energy point, if we take it over to the left axis, it gives us the critical depth. And if we take it down to the horizontal axis, it identifies what is the minimum specific energy required to convey this 10 cubic meters per second through a channel that's 4 meters wide. So minimum specific energy and critical depth are the first two things that we can figure out from this figure. It's important for you to know this. Like, this class a lot of it is just putting numbers into equations, but there are certain times when you're going to have to really understand what's happening, and this is one of them. I've given exam questions before where I just ask people to like tell me things from the figure, and it was really disappointing how few people really understood what's being displayed in this and what it means, because it's really powerful. So back to the idea of there being lots of different possible slopes, there are a lot of things that govern water's flow depth through a channel. Like everything plays a role. The roughness of the material that's been used, the shape of the channel, meaning whether it's trapezoidal or semicircular or rectangular and so on. All of these factors contribute, but for a given cross-section, it's the slope that determines what the flow depth will be. So all these different depths of flow that we see here would correspond to some certain slope. Now, alternate depths are something that we can diagnose from this figure. So remember, the first thing we can figure out is what's the critical depth. We can also, from this figure, we can find out if there are certain depths that seem to have the same amount of specific energy. So for example, when the water depth is 2.5, if we go over here to this figure, there is another depth down here. It looks like a depth of about 0.4 meters that has the same specific energy. And that is significant when we're dealing with a phenomenon known as hydraulic jumps. And hydraulic jumps are seen in a lot of cases. Maybe one that's really important to us is in the spillway of a dam. There are often hydraulic jumps where water is going from supercritical flow, where it has lots of velocity and a lot of energy. It will jump to subcritical flow, and it goes through a pretty visually dramatic transition, and it'll jump up to an alternate depth that we could predict using a specific energy diagram. Also, when water flows off of a step or up over an obstruction, these specific energy diagrams also predict what is going to be the new flow depth after some sort of a disturbance, like when the channel gets wider or when the channel gets narrower. These diagrams will predict what the new depth is going to be for adjustments like that. But an alternate depth is just, you can see that anytime you draw a vertical line through this curve, it crosses the curve in two locations. And so there are two different depths that have a specific energy of 1.5 meters. One of them looks like it's about 0.5. The other is 1.5 meters of depth. So those two depths have the same amount of specific energy. And so any questions so far about this specific energy diagram? This is called a specific energy diagram, and you're going to need to know how to make one. So flow regime can be classified using Froude numbers, or you can classify flow regime by comparing a given depth to this diagram. So any flow depth that's less than the critical depth corresponds to supercritical flow conditions. So when the flow depth is less than the critical depth, you have supercritical flow. When the flow depth is greater than the critical depth, you've got subcritical flow. So that's what this is saying. When the depth is greater than the critical, then that's subcritical conditions. Now, sub, maybe you'd be thinking, well, why is it called subcritical if the depth is more than the critical depth? It's because the velocity is moving slowly. If you've got deep water, it's moving slower. If you've got shallow water, it's moving faster. So when the flow depth is small, the velocity is high, and that's what makes it supercritical flow. So this is another way to diagnose the flow regime, is you compare the actual observed flow depth to the critical depth, and then you can figure it out that way. Sometimes we want to describe what is the top width of the channel when conditions are critical, so when it's flowing at the critical depth. So B sub C is just if the water is flowing at the critical depth. So if it's rectangular, then B sub C is the same as the bottom width if it's going critical. But when the channel is trapezoidal, we've got a trapezoidal channel and the water is flowing at the critical depth, then there is some top width that's corresponding to that. And we would say it's B sub C. So this is showing a rectangular channel. The B for a trapezoidal channel depends on the side slopes and then what the flow depth is. And the reason why I mentioned this top width issue is that one of the ways to calculate Froude number is with this formula here. So you could calculate it based on the velocity and the hydraulic depth, or you can calculate it based on the flow rate, the top width, and the cross-sectional area. So you could use this formula to solve what is the critical depth. So if the Froude number is equal to 1, you could set this equation equal to 1 and solve for the unknown depth. And that would be how you could find the critical depth, is numerically solving this equation by letting the Froude number equal 1. So we'll do that. We'll work an example where we solve the Froude number, solve for the critical depth by setting the Froude number equal to 1. When the Froude number is less than 1, it's subcritical flow. Greater than 1 is supercritical. And hydraulic depth, just to refresh your memory, this is something we've talked about before, but it's the area divided by the top width. So hydraulic depth tells you for a non-rectangular channel what the equivalent depth would be if the channel was rectangular, given the cross-sectional area that it has. So it's a parameter that you'd need to know in order to calculate the Froude number in terms of velocity. So the hydraulic depth of a rectangular channel is just its actual flow depth. So hydraulic depth is equal to Y if it's a rectangular channel. It's not equal to its actual flow depth in the case of a trapezoidal channel, though. Some channels are diagnosed as being very wide. And what we mean by that is if it's more than 20 times wider than it is deep, then the significance of that is if a channel is really, really wide, then it doesn't matter what the side looks like. It doesn't matter if it's rectangular or trapezoidal, because like if you let this be a very wide channel, then the hydraulic depth and the actual flow depth are effectively the same thing, because the cross-sectional area of the side components of the channel is insignificant. So we say very wide is when the width is more than 20 times greater than the depth. Then we could just assume that the hydraulic depth is equal to its flow depth, regardless of the shape of the channel. The hydraulic depth of a rectangular channel is just the flow depth Y. All right, so let's look at an example. First, solving using Excel, and then solving the Froude number. Just as a simple first case, let's consider a rectangular channel. We will do trapezoidal channels later on, but just to get a feel for things, let's start up Excel and try and make a specific energy diagram and find out when the flow depth is 0.25, whether we've got supercritical or subcritical flow, and then when the depth is 1.25, whether we've got supercritical or subcritical flow. So let me show you how to make a specific energy diagram, because you will need to do it for the homework eventually. All right, so we've got a bottom width in this channel of 4 meters. And then we're going to have a variety of different flow rates, a variety of different depths, a lot of different cross-sectional areas and velocities. And then we will calculate for each of these different depths what is the corresponding specific energy. Now you never know at the beginning how many different rows to have in a figure like this. You know, to have a nice smooth curve, you can't just have like 3 rows. That you'd get a triangle from that, not a curve. So, you know, like 10 to 20 rows is usually sufficient to get a good quality curve. So all of them is going to have the same 10 cubic meters per second flow rate. So let me just drag this down. But then we're going to look at lots of different flow depths. And we don't know from the beginning what should be the flow depth that we start with. So it's a little bit of an iterative process. Let's just see if we start at 0.2 and then 0.4, 0.6. So we'll do it in increments of 0.2 and see what that gets us. All right, so the cross-sectional area is going to be the depth, which I'm going to anchor that reference because it's always 4 meters wide regardless of which row I'm on, multiplied by the depth. So depth times the bottom width of the channel. So we've got a lot of different cross-sectional areas. And remember that the velocity is Q divided by the area. So Q divided by the area gives me the velocity. And specific energy is the depth of flow plus, remember, velocity head can be expressed as v squared divided by 2g or q squared divided by 2g a squared. And I'm going to do it that way just to get in the habit. So I'm going to say E is the depth plus q squared divided by 2g a squared. Okay, so that's the formula I'm using here on column E. So it's the depth plus q squared divided by 2 times g, so 9.81 times a squared. Okay, so I've got how much specific energy there is for 0.2 meters of depth, and when I double click here and it applies the same calculations to all of the different rows, now I've got what is the specific energy for each one. Let me clean this up a little bit. I'm going to decrease the amount of digits that are shown. Right now it's just kind of visually cluttered. You don't see what's important because there's just so many excessive digits shown on the screen. So let me reduce that down to a couple, and that'll be good enough. All right, so now what does it look like is our minimum point so far? What is the lowest specific energy here? It looks like 1.3 is the minimum so far, but that doesn't mean that that is the critical depth automatically. So let's just say, what is the value of y that yields the smallest E value? Okay, so what if I said 0.81? Well, it's hard to see. Maybe this one we do need to see a few extra digits on. 0.082. I'm sorry, 0.82. All right, got a little bit smaller. 0.83. Got a little bit smaller. Let me go and try under Data, Solver. I want this, so cell E7, to be minimized by changing the depth. So it's going to play around with lots of different depths, and it's always going to remember what is the E value associated with a given depth, and it's going to stop changing Y when it finds the smallest possible E value. Okay, so I'm going to click Solve, and really quickly what it'll do is play around with it, and it'll find 0.86047. Okay, so I want to keep that value, so I'm going to say OK. So now I'm going to change this. I'm going to say the critical depth is 0.0 0.860 meters. And the minimum specific energy is 1.2907 meters. All right. So far, so good. So let's make a graph just to show the specific energy diagram. I'm not going to bother with the diagram of depth versus velocity. That curve doesn't really tell us anything, but the specific energy diagram does. And so here, insert, and then I'm going to make an XY scatter plot where I smooth the lines, and I don't necessarily need to see the data points. So scatter with smooth lines. And so I'm going to select data and choose for the first series, X values ought to be specific energy. And then the Y values ought to be the depth. Okay. Let's see what we've got so far. Now, zooming out as far as we have, you know, where on the x-axis it's going all the way to 8, that means that we don't get to see this part of the graph as much detail. So it may be worthwhile for me to change the scale here. Like if I guess first of all what I want to do is add axis titles. So increase, let's add axis titles and clarify that down here on the horizontal axis, this is specific energy in terms of meters, and then on the vertical axis, this is depth, which we assign the variable y, and it has units of meters. Okay, and this is a specific energy diagram. And this specific energy diagram only applies to the flow conditions that we've described here of 4-meter wide channel, 10 cubic meters per second. Any other channel width, any other flow rate is going to give a different diagram. But what I was saying earlier about zooming in, let me right-click here on horizontal axis, and if I format the axis so that instead of going all the way to 9, what if we just focus in from 0 to 3? Then the advantage of doing that is it gives us a little bit more of insight in this part of the graph. So how many data points do we have there, by the way? If I have it show the points, that'll remind me, that's a fair number. We could put in a few more data points and that would make it a bit smoother. But this is a good specific energy diagram that, you know, we can see. Here's our critical depth. We could calculate alternate depths if we needed to. And here's what I want to reinforce to you as well, is that there's a certain part of this region that is supercritical flow and a certain part of this region which is subcritical flow. So I'm going to divide the graph up to, I'm going to do this line here just to emphasize that, anyway, let me make it a dashed line. Okay, so above the line is subcritical conditions and below the line is supercritical conditions. And so flow is subcritical above that line, and below it the flow is supercritical. Okay. If you tell your parents tonight that you were learning about supercritical flow at school, they'll think, wow, you're just learning really important things. It sounds important, right? Supercritical. And there's nothing more critical than supercritical. There's not hypercritical, not that I'm aware of. But the specific energy diagram is important for you to be able to prepare one. So now you've seen it. So when the flow depth is 0.25, okay? So when the flow depth is 0.25, that's down in the supercritical range. So we'd say that's supercritical. And when the flow depth is 1.25, that is more than the critical depth. So this dashed line corresponds to the critical depth. So I guess if I'm making labels, another label I could add here is, I'm making labels, I'd say critical depth equals 0.86 meters. So when the flow depth is 0.25, it's supercritical flow. When the depth is 1.25, it is subcritical. And if we calculate the Froude number, then that confirms it. So look at how the Froude number has been calculated. So the square root of the flow rate squared multiplied by the top width. So the top width will be 4 meters when the depth is 0.25 meters. G times A squared. So the cross-sectional area when we had that 0.25 meter. So if the depth is 0.25 and the width is 4 meters, then that gives you a cross-sectional area of 1. So the Froude number is above 1. So that also confirms supercritical flow. And then calculating the Froude number when the flow was at 1.25 meters of depth. So the cross-sectional area is greater down here in the denominator. Then the Froude number is less than 1. So that also reinforces that subcritical. So we can use either the graph or the Froude number to classify whether the flow is supercritical or subcritical at any particular point. Any questions? Like, why does it matter if the flow is supercritical? That's what you should be asking. You should always ask, so what? You know, like, why does it matter? Why are you telling me this? And the reason why it matters is that if the flow is supercritical, it behaves differently when it encounters an obstacle than it does if it's subcritical. So just the water reacts differently to non-uniform flow. So the reason why we have to be able to diagnose is it super or is it sub is because it's going to do different things when it encounters like a drop off of a cliff or a change in slope or a channel getting wider or narrower or a step up or a drop down. Any kind of interruption to uniform flow, whether it's sub or supercritical before that interruption, before the obstacle, is going to dictate how it reacts. That's why it matters. Yeah.
So if we were designing this channel specifically, and we told them to build it to 0.8 or almost 0.9 in depth, would we rather them accidentally build it taller so that way it's in subcritical flow?
Most of the time channels are built, the flow is subcritical, and that's because the slope that the channel is built on is usually relatively flat. So as a hydraulic designer, you don't usually have control over the slope. It's just the topography is in charge of that variable. And where you get to choose, like there may be rare cases where you can decide where the channel is going to go and you could pick a route that forces subcritical or supercritical conditions. But they usually only have supercritical flow on purpose in a few select locations. Because if the water has that much velocity, chances are it could do some damage. It could do like scour of the channel. So usually they're pretty cautious about having the water flow under supercritical conditions. And then they'll have some sort of, downstream of the supercritical flow, they'll put like big blocks of concrete and they'll reinforce the channel. They'll have some place for it to intentionally go through a hydraulic jump so that it can go out of supercritical flow and back into subcritical flow conditions.
So I forget the name of that big spillway that we looked at, the whole hillside collapsing.
Yeah.
So was that, when it comes out, is it in supercritical and then their whole slow it down.
The Oroville Dam?
Yeah.
Well, yeah, let's look at those pictures. I don't remember where those were, which lecture.
First one.
Very beginning.
What is it? Feels like a lifetime ago. Here it is. Yeah. It's not that they're intentionally trying to make it supercritical through that spillway. It's just that, you know, that's, I think, the steepest dam in the United States, and so it just kind of, by virtue of the size of the dam, it's supercritical over that, yeah. But remember, the water only flows over that spillway once every 25, once every 50 years. Most of the time, the water's going through their penstock, which is like these big pipes that run through the hydroelectric plant. But yeah, that's definitely supercritical flow, and that's, you know, part of the reason why it caused as much damage as it did. You know, the concrete had some flaws in it, and when water is moving at really high velocities, then it's going to find whatever weakness, whatever flaw in the concrete, and chip away at it. There's a lot more energy for it to do scour. But, you know, there is like these big blocks down at the bottom. Let's see, do we get a good picture of those? Yeah, this is meant to kind of slow the water down a little bit, but even when it gets into the channel downstream, it's still going to have a lot of scour energy, and so it would, even if the spillway wasn't broken, if they have to use the spillway, there's going to be damage to the river downstream because there's so much energy in the water. All right, here we are. All right, 1:49. We are out of time. So here's what we'll do when we get together on Wednesday. Is we're going to use a specific energy diagram, the same one that I just made. We'll come back to it and we will ask what is the alternate depth for when the water is flowing at 0.5 meters. So we'll play around with this. I'm going to save it so that I can come back to it again. If you've got yours, save it so you can come back to it again. We'll just revisit this example on Wednesday.